Okay, so I welcome you all, and in continuation to our yesterday's discussions we had on particle in a finite potential one-dimensional box, right? This is the problem that we have been discussing, we have been talking about. We started with the potential, we chose the finite potential in both the sides, and then the potential of the particle inside the box is taken as zero. We used Schrodinger's equations, we wrote down Schrodinger's equations for three regions, region 1, region 2, and region 3. And before proceeding on that, before proceeding on the given problem that we have been talking about, we started our discussions with a particle in an infinite potential well, right? This is what was our starting argument. But is there something that we can think parallel to this infinite potential well problem? As you saw that when we resolved Schrodinger's equation for particle in an infinite potential well, what you realized that there are certain important points, bound states where the particle can be, okay? And you observed that there is a constraint. That constraint is developed by what? By this infinite potential. And it's the infinite potential which is dictating this particle how it has to remain inside the potential. And what is that? It is purely harmonic in nature, and there is discreteness in the energy. Now think about a free particle. A free particle has all plausible energies. It can do anything it wants to do. This is not how the nature works. This is not how the universe works. I believe that if one particle can do whatever it wants to do, it will not allow the universe to exist. So, can we have any example that we can correlate with this hypothetical problem of infinite potential? Well, this is my question to you. I think yes, even though the framework of problem is different, but we define the stability of this universe using some important celestial objects. And these objects are called what? Black holes. Now, what is a black hole? Doesn't it seem to have the same kind of symmetry with respect to a particle in an infinite potential well? No doubt, these are the two different frameworks. In a black hole, you have the warping of space and time, okay? And here you have the potential, infinite potential. And for the particle to be inside this well, it is impossible to leave the well, right? So we can correlate the problem of this infinite potential to the problem of black holes, right? And here we have infinite potential. In the black holes we have event horizon, okay? So here the potential is dictating this particle that what it can have and what it cannot have, right? But there the problem is very, very complicated, but it seems to have the same symmetry. The only difference being that here you have gravity involved, because gravity is the warping of space and time, right? And the particle that exists in these black holes, right? We can imagine them to be somehow correlated with the particle in an infinite potential, right? So you have dictation here. If you think black holes quantum mechanically, You can have dictation in the black hole. But gravity is, we fail to make gravity quantum mechanical, right? We cannot treat gravity quantum mechanically. That's the big problem of the physics. That's why there is no unification. There is no unification of quantum laws with the gravity. You cannot describe gravity using quantum mechanical laws. So this is how you can look for the examples, the real world examples, the real universal examples that will match your ideal system, right? That will match your ideal system. This is how physics works. You come up with an assumption. If it works, it becomes the law. If it doesn't work, come on, you can leave it. Or you can have a person who will come up with a better theory. So we have been talking about the finite potential well, and we are giving this particle a chance to leave this potential. Okay, so we have described this problem mathematically, and what we obtained the even solution and the odd solution. So what was the even solution? The even solution was psi
of x is equal to AE.
Yeah, this is a framework of what? E to the power of
K1 of x.
K1 of x, then
E cos K2 of x.
yeah, E cos K2 of x, right?
DE to the power
dE to the power
minus K3 of x.
minus K3 of x. Very good. So this is your even solution. Okay. So if you want, you can resolve this even solution. And if you remember, the problem is like this. In our case, the choice is yours. We had chosen this as minus L by 2 and this as L by 2. And here this V naught is 0 and here it is finite. Okay? So it is finite in the region 1, it's finite it is 0 in the region 2, and it is finite in region 3. Right? Now see, as I told you, even when you will go in quantum mechanics second in your next semester, you will be dealing the same problem, what we call as quasi-classical case, because it's a mixture of quantum mechanics and classical physics, because this is something which is very complicated, and it cannot be resolved. It cannot be resolved, this point, and this is called turning point. Okay, so here we don't have to talk about the same problem in terms of that story, but what we have here at x is minus L by 2. So for the eigenfunction, it is important that if I want to describe these two regions for psi 1 and psi 2, because you will have psi 1, then you will have psi 2, then you will have psi 3. So between psi 1 and psi 2, what is important for the wave function to be physically acceptable? It has to be continuous, right? So to make it continuous, what I will say that this psi 1 at x equals minus L by 2 must be equal to psi 2 at x equal to minus L by 2. Am I right? Okay, this is the way mathematically I can write down this connection between the region 2 and region 1. So if this is the case, if psi, okay, what is psi 1 now? I can write down that A e to the power of K1 minus L by 2, right? And give the value of x here, okay? Will be equal to, for psi 2 I have E, yeah, cosine of K2 minus L by 2. Okay, minus L by 2. Right? Fine? Okay. And you know this cosine will absorb this negative, right? Okay, that's the point number one. Okay, now for psi to be continuous, psi 1 must be equal to psi 2. But if psi is continuous, there is another important condition. What's that? The derivative of psi has to be continuous, right? So if the derivative of the psi has to be continuous, what you are going to do here is, you take the derivative of this. Okay, what will be that? That will be a k1
e to the power
minus, e to the power of
k1
k1. I have given the value of x, okay? This is minus L by 2, and this will be equal to k2. E, cosine will give us minus sine, okay? So this will give us minus sine k2 of minus L by 2. Okay? So you will take care of negatives and positives. And you can immediately see that if I have this as equation 1 and this as equation 2, what will happen? You will divide these two equations, because you can see this will give me tan theta, right? So this and this will cancel, okay? So A and A will cancel, E and E will cancel. So what you will be, have you written it down? Or should I wait a little bit? Okay. Yeah. Okay, so you'll be dividing these two equations, and what you will have k1 equals k2 of tan of k2 times minus L by 2, right? This is called a transcendental equation, okay? So you see, what we have done, we have this transcendental solution in terms choosing the even solution, okay? Isn't it? Now, we will do the same process in terms of odd solutions. We'll do the same thing in terms of odd solutions. Now, who would like to write down? Yeah? Yeah? Come on. So you give me psi, okay? You give me psi, so this is my equation 1. And for that, I will write down the psi for odd solution. What's that? That's a framework of ae to the power of
k1 of x,
k1 of x, and then here f sine k2 of x, and then
d to the power minus k3 of x.
okay, e to the power of minus k3 of x. This is it. Okay, the same way we would like to resolve this problem, because psi has to be physically acceptable. So psi, for psi to be continuous, psi 1 at x equal to minus L by 2 will be equal to psi 2 at x equal to minus L by 2. Isn't it? Get it? Okay? So I'm treating the same problem. No? I'm taking the odd solution now. Okay? Previously I took the even solution. So when I take the odd solution, what will I get? What will I get? Can you tell me directly what I'll get? Okay, here you will have the same thing. E to the power of k1 x will be equal to f sine k2 of x. Isn't it? Okay? And for x you will give minus L by 2, okay? And you will take its derivative, because the derivative has to be continuous. When you will take the derivative, what you will get? You will get cosine, okay? So in the previous case, you got rid of negative here. In this case, the negative will exist, because sine will not absorb the minus sign, right? So can you tell me what I'll get here? Come on, you're good guys. You can tell me. Yeah? Okay? You can do it. It will take a moment. It will take a minute. Okay, what will be that? That will be K1 equals minus K2 cot K2 of minus L by 2. Isn't it? This is what you will get. You can get it easily. No, not so complicated. Now, see, it's impossible to solve these equations. And these equations can be resolved graphically, right? So we would like to take the graphical root of these equations, and we would like to interpret the results of these equations. And in doing so, what we have now, we have these transcendental equations. Okay? Okay. When you will plot these equations, what we will observe, and the problem is that the board is so harsh. Okay, now you have these two equations. If you come up with assumption like z equals kl by 2 and z naught equals L by 2 under root of 2m v naught by h bar square, and taking this k as an approximation, so you will have to make certain approximations so that I come up with k, and when you will do that algebra using these equations, you will obtain two equations. What you will obtain? You will obtain something like this: z tan z equals under root of z naught square minus z square, and z cot z equals under root of z naught square minus z square. This is what you will obtain. You have to make the manipulations, and these manipulations will lead you to these two equations. Now, what is good about these two equations? What's good about these two equations is that the right-hand side of both equations is same, and the right-hand side of both these equations is representing what? It's representing a circle. It's representing a circle. Okay? Okay? So these are the two results that you are going to obtain. Now, that means, now what's my target? My target is the graph here, okay? What was the reality of the particle in infinite potential? Well, the particle could have all possible energy levels. There was no limit on the number, okay? But here, you will see that when we extrapolate these equations on the graph, we find there is a limit. And that limit okay, so how will it, okay, it's a bad line. Okay, so this is even, odd, even, odd. So these curves are representing your even and odd, okay? You know that tan z is coming from even and cot z is coming from. So this will be your even, so that means it will be like z tan of z, and this is coming from odd, so z cot of z, okay? And what was in the right hand side of the equation? the circle. Okay, so there you have certain limits. The limit one, say for example, if you take this in terms of angles, so this is 0, this is pi by 2, this is pi, this is 3 pi by 2. You will have to check this yourself. Okay. Then for the first case, if I draw that under root of z naught square minus z square, that will give me a circle like this. And for another angle between pi by 2 and 3 pi by 2, if I draw it, I will get another circle. And between 3 pi by 2 and 2 pi, I will get another circle. Now what do you find here? You find the intersection. Okay? So in the first case, you will have, what is this line? This is even line. Okay? This is giving you the bound state, one bound state. The minimum that you can have here is one bound state. And this dot is telling us that it's a bound state, right? Now for the second, how many bound states? Two bound states. One is even, another is odd. Do you see? This is basically what? I'm drawing actually a circle. As I said, the right hand side of that equation is telling us that it's an equation. It is representing a circle. So these circles, when you draw these circles, you obtain these bound states. What do you obtain? So in the first case, you have one bound state, that's even. In the second case, you have two bound states, even and odd. In the third case, you have three bound states, even, odd, even, and you will go on and on. But you will have a limit. Is this clear? You can resolve it, you can work it out on your book. Can I rub it?
Yes, sure.
While resolving this problem, manipulating all of these equations, what approximate value we can get for these bound states? Now, if I say n is the number of what? N is the number of bound states. Bound states. The particle can exist at these states. It's reflecting the quantization of energy. It will have only these states that we were trying to draw here. I couldn't make it beautiful, but still I tried to make it that way, the way it is. So this n, it comes to be 2L by pi under root of 2m v naught by h bar squared. This is the main equation that we are interested in, because it certainly gives us an idea about the number of bound states. Okay, what I said, what's our problem? Our problem is that we are dealing with a particle, this particle in a one-dimensional box, but the potential of this one-dimensional box is finite. Okay? Finite means it is not infinite. But finite also means less than infinite. Right? So we need to have an equation that will give us an idea about the number of bound states, because you can choose a potential that is close to infinity. Okay? You can choose a potential that is very, very small. Okay? So for that, you can see that we have this equation. Okay? And this equation is telling me what? This equation is telling me that the number of bound states is proportional to what? Come on. It is proportional to under root of V naught. That means if your potential is more, the number of bound states that you will obtain will be more. Are you getting my point? Okay? If the potential is small, the number of bound states will be small. But if you choose the smallest potential, how many bound states you will make? You will make one. Okay, so there is another constraint. Okay, there is not anything like zero here that automatically connects to your 0 point energy kind of thing. Okay, then there is another important result of this equation, that this number of bound states is proportional to the L. What is L? L is the width of this potential, right? So if the width of the potential is large, the number of bound states is large. Are you getting my point? Huh? So both the things are clear at this point of time, that if your potential that you are choosing, if it is more, you will have more number of bound states, and the minimum number of bound states that you can have is 1. Okay? If the width of the potential is large, you will have more bound states. This is what we expect, which is basically a deviation from that infinite well potential. Because in case of infinite well potential, you have no limit. But here you have the limit. Okay? Anything else? You got this?
Yes.
Okay, so I want you to actually do that algebraic mathematics. You can just make a multiplication and division, and you can use the book to obtain these results, because you can treat the same problem in some approximate analytical way. But here I tried it to give you an idea about the problem. I chose the graphical way to interpret the result of this problem. Okay? So with this, any questions if you have? You didn't feel fascinated about the black hole? No? Didn't raise the questions? Okay, so